Hello wonderful person, this is Anton, and today we're going to continue our discussion of the so-called Fermi paradox, the paradox of not seeing anyone out there, any other intelligent extraterrestrial life. And today we're going to discuss a new paper that seems to find yet another solution to the Fermi paradox by proposing the reworking of the so-called Drake equation. The famous equation that tries to calculate how many potential extraterrestrial intelligences there should be in the vicinity. So let's talk a little bit more about this, and welcome to What the Math. There have actually been quite a lot of versions of the so-called Drake equation in the last few decades, and a lot of them do come up with very different results. But most of the time the results suggest that there should be actual civilizations around us, or at least somewhere in the galaxy. But every once in a while we do have to rework the equation simply because we collect more data in regards to various exoplanets out there. As of 2020 we've discovered over 4,000 different exoplanets, and we now have a pretty good picture of how many different types of planets there are, and also what kind of stars usually have these terrestrial planets, and how many of these stars do often have terrestrial planets in the habitable zone of their planet. And using a lot of the modern data, the scientists behind this paper proposed that there should be around 36 different so-called SETIs, communicating extraterrestrial intelligences in the Milky Way galaxy. But why do they think so? How did they come up with this? And most importantly, why can't we hear them? A lot of their ideas are based on the modern understanding of the galactic formation and the formation of stars in different galaxies. Most importantly, it involves the idea of metallicity. Metallicity in astronomy refers to, well, pretty much everything except for hydrogen and helium. Hydrogen and helium are non-metals, whereas everything else is considered to be metals. It's a very strange name, but that's kind of how it works. The thing is, today we know that planetary formation depends on metallicity. The more metallic the star is, the more likely it's going to have terrestrial planets and even other planets orbiting around it. Stars that are low in metallicity will either have gas giants or might not even have any planets at all. And when it comes to metallicity in galaxies, today we even have this term known as the galactic habitable zone. Essentially, in a typical galaxy, we think that the inner part of the galaxy is not really habitable. First of all, it has low metallicity. Second of all, it's usually very active and has a lot of different flares going on, usually from the black hole itself. And most of the stars on the outskirts are the only areas where we can actually possibly find terrestrial planets capable of supporting life. So in order for us to find life somewhere, we need to be looking at areas of high metallicity and probably away from the black hole itself. All of this kind of comes into consideration when trying to work out this new Drake equation, the 2020 edition of Drake equation. And for this particular study, they took what we know about planet Earth to try to discover similar other locations somewhere in the galaxy where obviously similar conditions could lead to other life, similar to the one we have on Earth. In other words, they are looking at stars that are about 5 billion years old, or anywhere from 4 to 5 billion years old, and they're also looking at stars where habitable zones and metallicity are very similar to the ones in our own solar system. So basically, what the scientists behind this paper are trying to discover are the replicas of the solar system in our own galaxy. But there are actually a few more important features in this new formula that weren't really present in other ones. One of them is in regards to how long it takes for life to evolve on a similar planet, and here they try to keep it very similar to planet Earth. But the other one is in regards to how long a civilization can last. Basically, how long it takes for a civilization to survive and to stay technologically advanced before potentially going extinct. And this is really the important part here, because the scientists behind this paper make a very important assumption that it's very likely that many civilizations do go extinct. But before they go extinct, they make an assumption that an average civilization will have at least 100 years of communication using very similar devices to what we have here, or basically electromagnetic communication, using radio waves to communicate with the rest of the world, and of course the rest of the galaxy. So in other words, they make assumption that somewhere out there are similar species to humans that are trying to reach out and are trying to search for extraterrestrial intelligence, living on planets very similar to planet Earth, around stars similar to our own sun. And one of their more strict assumptions here is that their planet has to be about 4.5 to 5.5 billion years old, and they're also in a very similar stage of advancement and in a very similar stage of their intelligence to humans. So if we take all of these numbers into consideration, we actually come up with a number that's about 36, with the lowest number being 4, the highest being over 200. And if all of them are equally distributed across the galaxy, this also means that the nearest such civilization to us is going to be at a distance of about 17,000 light years away, with the closest distance potentially being 7,000 light years. And this is of course where we have our resolution of the Fermi paradox. First of all, the number of active communicating civilizations will directly depend on how long they're able to communicate for. If on average a civilization is only able to send radio signals for about 100 years, we will probably find an average of about 36 active civilizations in the galaxy right now. However, if it's, let's say, 1,000 years, this number will go up to a few thousand civilizations. So this really depends on how long the civilization is capable of, well, essentially surviving. And this is kind of where we also come to a very important conclusion from all of this. Because we don't seem to detect anything right now, it suggests two things. Either that, well, basically we're alone, or that civilizations don't seem to survive for a very long time. They don't seem to survive long enough to transmit messages for really long periods of time. Because we're not finding any active civilizations in our galaxy right now, it's a really bad sign. It just means that we might not really have a long-term existence in this galaxy. And so this could actually indicate our eventual fate as a species, as an intelligent, communicating species able to create these messages that travel across really vast distances. However, it doesn't mean that we're going to be going extinct anytime soon. Even according to the most optimistic calculations here, the closest such communicating extraterrestrial intelligence to us would be about 1,030 light years away from us. This is the best case scenario. That's actually double the distance to the famous Betelgeuse. And if so, that also means that it will take us about 2,000 years or so to establish an active two-way communication. And that's just not practical right now. However, for this best case scenario, if the average life of a typical civilization is less than 1,030 years, the average separation between stars becomes much too great for any communication to actually happen. In other words, the neighboring civilizations will never be aware of each other before going extinct. And one of the major explanations here is that, well, maybe if a civilization develops the technology to communicate over really large distances, it's also kind of related to technology that can also then sort of extinguish the species itself. In this case, what you're looking at right here, the rocket, was originally an ICBM. It was meant to be a destructive tool that would cause huge nuclear explosions across very vast distances, and it's really lucky for us that we were able to develop this destructive technology and create something useful out of it, and maybe some other civilizations were not as lucky. Maybe they actually ended up destroying themselves completely. But this is basically just one of the many explanations for why civilizations that develop communication might also be able to accidentally destroy themselves. And so this so far suggests that even though it's very unlikely that there are these really long-living civilizations that communicate for many thousands and even millions of years, it's quite likely, or it's quite possible, that civilizations with much shorter civilization lifespan might be all over the place. There could be up to 1,000 of them in our galaxy alone. But the assumption here is that life develops always the same. It's always very similar to how it developed on Earth, and it also always leads to the same advanced civilization that wants to communicate with the rest of the galaxy. These are really big assumptions. We don't really know if that's true. And even though technically a civilization can extend its life by moving to another planet, like for example, if we as humans somehow manage to move to Mars one day, we might be able to extend our existence a little bit as well. At least that's the assumption here. But the scientists in this paper speculate that even this might not really prolong the existence of a civilization long enough for the interstellar communication to occur and for one of the civilizations to be able to hear another. So the resolution to the Fermi paradox here is that we're just really far away from one another. And just to give you a comparison here, over the last few decades, the entire SETI search has only scratched the surface here. If we were to consider the entire galaxy to be the oceans of planet Earth, over the past few decades we've only seen the equivalent of this tiny tank of about 8,000 liters. So basically, we have only sneaked a peek at the entire galaxy. We've barely seen anything and we've barely had time to look around us. And this is mostly because of the limits of the speed of light. But I guess the saddest discovery in this particular paper is that, well, it seems like unless we manage to survive for thousands and thousands of years and be able to communicate for so long, it's unlikely that we're ever going to hear anyone, at least mathematically speaking. In other words, this paper suggests that search for extraterrestrial intelligence will very likely fail. But nevertheless, there are a few really interesting discoveries in this paper that are sort of promising. For example, the scientists in this paper suggest that there could be tens or even hundreds of billions of different planets that do have primitive life, or life that's not really trying to communicate with anything, that's just trying to survive somewhere out there. And we do have a very high chance of finding it if we keep looking, and also if we try to become an interstellar species and land somewhere out there on another planet. At the same time, they suggest that the peak of life in the galaxy, or basically when there was most civilizations out there that were able to communicate, was roughly around 5 billion years ago. In other words, we currently live in the times when there's actually a decline of these active civilizations, and it's probably going to be following even more in the future. So essentially, we could be one of the later species out there, assuming of course that all of the life everywhere forms in a very similar way. They also calculate that we would need approximately 3,060 years to discover any extraterrestrial intelligence using a program similar to SETI, and the same would be true for other civilizations as well. So basically, if there are species out there looking for others, it would take them roughly around 3,000 years to discover someone else out there, and to be able to communicate with them, they would probably need even more. But one of the more important discoveries here is that, let's just say that we don't discover any extraterrestrial intelligence within about 7,000 light years away from us. This is a really important discovery because it means one of two things. It implies that the lifetime of a typical communicating civilization is less than 2,000 years. We've only started doing this, so ours is only about 100 years, so we do have at least 1,900 years to go. However, that also means that at some point we might be able to go extinct, as many other civilizations have done so in the past. But the second assumption here is that life on Earth, and life in general, is just extremely rare, and life on Earth is indeed unique and does not automatically form on other similar objects. This is a really important assumption as well, because right now we don't really know if life is even possible on other objects, other moons, other planets. And discovering it somewhere out there might definitely give us a hint on what's going to happen in the next few thousands of years. In other words, this search for extraterrestrial intelligence is actually sort of like us trying to determine what's going to happen to ourselves in the next few hundreds and thousands of years. Are we going to be able to survive this, or are we going to go extinct like dinosaurs? And this of course also implies that the so-called Type 3 life, or artificial life that was created by the original creators, might also not exist. So even though some of us do dream of living forever and possibly even transferring our intelligence into something else and thus prolonging our lives indefinitely, it might not actually be possible, assuming that this is what everyone else does in the galaxy, because once again there doesn't seem to be anyone out there. And if these unusual species, these immortal robots existed, then we'd definitely hear at least a few of them trying to communicate with someone. And that's unfortunately not what we've been seeing so far. And so even though this paper does suggest that our search will eventually fail and that we're not going to be able to find anyone, and also that there's a big chance that we might not also survive ourselves, it is in a sense a very important message. It's a message that we need to be aware of our own existence and aware of the potential for our own demise. It's really important for us to understand that if this is indeed what's happening around the galaxy, there might be a chance for at least one civilization to prevent its own disappearance. And this could be us. Maybe we could be the first civilization out there to outlive our own potential destruction and to become, basically, the first ever Type 3 life. Civilization that does last for a very, very long time. But right now, all of this is of course just speculations based on mathematics and based on our observations of lack of everyone or anyone out there. And if you'd like to learn about another very interesting view of Fermi paradox and how it can be resolved, check out the previous video I made where I talk a little bit more about how civilizations might progress in a different direction. But anyway, once we discover more about aliens or really anything related to space sciences, I'll make sure to follow this up with another video that might help us understand what's going on. Until then, thank you for watching, subscribe if you still haven't, share this with someone who loves learning about space and sciences, and also feel free to read this paper, it's in the description below. Come back tomorrow to learn something else, support this channel on Patreon, maybe support this channel by buying the Wonderful Person t-shirt that you can also find in the description below, but either way, I'll see you tomorrow, space out, and as always, bye bye.